So those of you who were not present in the first lecture, you can ask me any questions you have. Also, the recording of the first lecture is uploaded, so you can go on Blackboard. If you go to the course and course contents tab, you will see the class recording. You should be able to find the class recording, right? But if you have any questions, please reach out to me. If you need the syllabus, please go on Blackboard and you will find the syllabus in the syllabus tab, okay? And yeah, I guess that's it. So let's go ahead and start the discussion. We are going to start by a very simple introduction to heat transfer. And this is a very uncomfortable desk. So introduction to heat transfer. The first thing you want to know when you are dealing with heat transfer and energy transfer, essentially in general, is what do we mean by heat transfer? And I'm assuming at this point in your career, all of you have some sort of an idea of what heat transfer is, right? So anyone care to jump in? What is heat transfer? When you hear the words heat transfer, what comes to your mind?
Thermal energy exchange.
Thermal energy exchange. Okay, one, Daniel. Thermal energy. What else? Temperature difference. What else? Anyone else?
Loss of heat with the surroundings.
Okay, could you repeat what you said?
Loss of heat with the surroundings.
Loss of heat to the surroundings. So essentially, all of you are moving in the right direction, right? We essentially, when we say heat transfer, we mean the transfer of energy between two different locations. And that transfer of energy is because of the difference in the state of energy in that two locations, right? That difference can be, we usually call it a temperature difference, right? Temperature is a representative of internal energy of the system. So if there is a difference in the internal energy between two locations, you will see a transfer of energy. Whenever we are talking about the heat transfer, this is essentially what we mean, right? There are different types of heat transfer. This definition of heat transfer specifically talks about sensible heat transfer. To make it, I guess, more sensible, let me give an example. Let's say there are 2 points with different temperatures, T1 and 2, and they are not equal. We will have some transfer of energy, and that transfer of energy can be identified with the total energy transfer can be identified with this very famous formula. M, the mass of the total system, multiplied by C, multiplied by the temperature change. Right? So if you heat up something, even they don't have to be in two different spatial locations. It can be a different state in time, right? So total energy transport, total energy that is transferred between the two states is a function of mass of the system, a specific heat of the system, and the temperature difference between the two states. There is another form of energy transfer, heat transfer. which is called the latent heat transfer. Is there anyone in class who wants to explain to us what latent heat transfer is? And what is the difference between a sensible heat transfer, or sensible heat in general, and latent heat? No one? Do we know what latent heat is? Show of hand? No? Okay, so that's all right. Sensible heat, the heat that is transferred due to temperature change, right? You can sense the energy difference. If you feel at like 20 degrees Celsius surface, it is going to feel different compared to 40 degrees Celsius. Yes?
I just had a question. Would latent heat be like the one associated with the phase change?
Exactly. So when we are talking about the latent heat, we are talking about a type of heat transfer that you can't really feel. And by that I mean you can't really feel the energy difference between the two states, right? This is where phase change comes into play. You can't really feel that water vapor has a different energy state compared to a saturated liquid, right? Both of them are at 100 degrees Celsius, right? So you can't really feel the energy difference. The energy difference goes to molecular bonds. There is still energy difference. The reason we have the heat transfer is because we are putting in enough energy to break the molecular bond. So the energy state is going to be different. The energy between the two states is going to be different, but we can't feel it, right? Now, how can we identify, or how can we calculate the energy that is transferred between the two phases? If it's evaporation process or condensation. So evaporation or condensation, meaning that we are going from gas to liquid or vice versa. Then your heat is going to be, total heat transfer is going to be equals to m dot multiplied by the heat of vaporization. This is called the latent heat of vaporizations. Which essentially is the amount of energy needed to evaporate a unit mass, which is 1 kilogram, of any liquid, water or any other liquid. Right? It's going to be different for different liquids. Or the other way around. How do we find this value? How do we find this energy? We essentially measure the enthalpy of liquid at the saturation temperature. And I'm assuming you are already familiar with enthalpy, with just the terminology, and the saturation temperature. If you are not, you're always welcome to ask questions. An enthalpy of gas or vapor at that same temperature, at the saturation temperature. Then you subtract them. That's it. This is how you can find the heat of vaporization. Or we actually, in thermodynamics, they usually use H of Fg for it instead of VR. The same concept applies to phase change from solid to liquid, right? Which is called either solidification, depending on the process, or melting, right? So heat of solidification is going to be equal to m dot H of SL. Any questions so far? Simple and plain. We have two types of heat transfer. General idea of heat transfer, we have two types. It is either sensible, meaning you can sense the energy difference, the difference between the two states, or latent, that you can't really understand the energy, you can really see the energy difference, but there is energy difference between the two states, right? Okay. If there's no question, let's move on to the next topic. So we understand heat transfer, we understand different types of heat transfer, general idea of a heat transfer. But what we haven't defined yet, or we haven't understood yet, is temperature. This is something that we have been dealing with throughout our education here as mechanical or aerospace engineers, right? We have here, or chemical engineers, or whatever, right? Temperature. What is temperature? What is temperature? Or how is this defined? Let's go one by one, because I want everyone to jump in here. If you were not here for the first class, I should tell you that I usually do this, so don't be stressed. You don't need to give me a right answer. I just want to know what you're thinking. There is no grading here. What is temperature? If you don't know, that's all right. You can say, I have no idea.
I can try.
Sure, go ahead.
Average atomic collisions at molecular scale.
Average atomic collision. Right?
Right.
Okay. What is temperature? You have to be quick, guys. If you don't want to contribute, that's all right. Just say, I don't know.
I don't know.
Okay. What is temperature?
I have no idea.
You have no idea what temperature is. Okay. We'll come back to you. Let's do a full run.
It's a thermodynamic quantity.
What kind of quantity? Thermodynamic quantity. Thermodynamic. Well, what does it represent?
How much heat present in the body?
How much heat is present in the body, huh? In the object.
Object, yeah.
Okay.
I don't know.
I think it is a quantity, physical quantity that measures the degree of hotness and coolness of the body.
Degree of hotness. Okay. We don't have degree of coolness, right?
Hotness or coolness.
Or, I mean, don't, okay. Thanks. Daniel.
Yeah, like the average atomic collision thing, it's a measure of like the kinetic energy on a
We
molecular
have
scale.
2 votes for this. Is this true?
Oh yeah, I was saying it's like the average kinetic energy on a molecular scale.
Average kinetic energy. So this
Which
is not.
isn't like quite true, but
It's an average kinetic energy of each molecule.
or sorry, the measure of the kinetic energy.
Well,
Yeah,
I'm gonna go by average.
Okay.
I don't want to go back and rewrite it. Measure of internal energy. Next one.
I agree with the idea of the degree of happening or occurrence.
2 votes for this.
I was going to say how much heat is present in the objects.
Okay, 2 votes for this.
Measurement of chaos in
Measurement of chaos. How
a molecular level.
do you spell chaos? That's CHAOS, right? Okay.
Another vote for the internal energy.
Internal energy. Okay.
I have no new idea. I think internal energy
Internal energy. Thank you. Next. Okay.
The amount of heat that's in an object.
Amount of heat that is in an object. So 3 was here. So those of you who responded with this, average kinetic energy or internal energy or even chaos, are correct. So temperature. But when you say amount of heat preserved in a body, that doesn't really tell us any new information. It's just a different presentation of the same idea, temperature. It's just a different name for temperature, right? Well, the temperature itself is a representation of internal energy of the system, which itself is a representation of average kinetic energy of each molecule. Or kinetic energy is essentially how fast or slow your molecules like move. Or, I mean, I don't know if you can relate it to the chaos there, but yeah, so kinetic energy. So based on this idea, when we define temperature based on a molecular level phenomena, we have to go back and have a molecular level look at things, right? We should be able to define temperature based on the molecular level properties. So the next part of this introduction is a molecular level presentation of energy transfer and heat transfer. And this is where we are going to introduce kinetic theory of gases. So we are going to use the kinetic theory of gases to be able to characterize the movement of molecules, right? Movement of molecules is very chaotic. So it is not possible actually to characterize the movement of individual molecules, not for us at least. So what we're going to do is that we are going to have a statistical look at things. What does this mean? This essentially means that we are going to look at the averages. We are going to make a lot of assumptions about the molecules. One of the assumptions we are making here is that the molecules are always moving. Hence the name kinetic theory, right? So molecules, and we are talking about gases here specifically. This is kinetic theory of gases. We are going to expand this to cover liquids and solids a little bit later. But right now we are only interested in gases. So one of the assumptions we are going to make is that molecules are always moving, right? And they spend most of their time essentially moving from one collision to another. So essentially, let's say this is a pool of gas, and there are molecules present here. What happens is this molecule moves here, collides with this molecule for a very short amount of time, and then changes its direction, moves to either collide with a plate or another molecule. But most of its time is spent just moving in a straight line or moving on a straight line, right? Why is this the case? Because we are assuming the gravitational effects on molecules and each molecules are negligible. All of these assumptions for gases are pretty decent assumptions. They work very well. So we are not making it that simple. It's just a very realistic representation of what happens inside the gas. Okay? So what we want to do here is to somehow relate this motion to this new quantity temperature. So we have to find the kinetic energy first for the whole system, then we can relate it to the temperature of the system. You have to keep in mind that temperature for each molecule doesn't really mean anything, right? Temperature is a macro scale thing, right? We define temperature for a pool of liquid, right? For each molecule, for a pool of gas or solid or whatever, right? Each molecule has an energy state, which in gases is going to move some sort of a movement, right? And what happens to molecules in solids? Can they move freely? No. What happens? They only vibrate, exactly. What about liquids?
They can
Move around a little more.
They are connected to other molecules, right? So the molecular bonds are pretty strong there in fluids. They can move a little bit, and they can also vibrate, and depending on the liquid, let's stick with translational and vibrational motion. But in gases, they can vibrate, they can move, and they can rotate, right? But since the movement is so dominant here, we are just only going to focus on the movement of the gas molecules. So we are just assuming this kinetic theory representation, we are assuming the rotational and vibrational energy are negligible. We are not going to talk about them. Let me put it this way. So the first thing we need to, let me ask you this before moving on. Let's say we are talking about a car, not a molecule. How can we find the kinetic energy of a car that is moving? Kinetic energy of a moving car, of a moving object.
The mass is mass and its speed times
That's it. It's a very famous formula. You have seen it many times. So essentially, to find the kinetic energy of these molecules, and then to find the kinetic energy of all of the molecules, which is a representation of their internal energy and temperature, we somehow have to find the speed of the molecules. And since we are doing a statistical analysis, we have to find the average speed of the molecules. And we are not going to go into the proof of this, just accept it from me, that the average speed of the molecules, C bar, is the square root of 8 multiplied by a constant, K of B, multiplied by the temperature of the bulk of the fluid, right? Bulk of gas bulk, divided by pi divided by M.
is that the speed?
That's the speed. That's the average speed of a gas molecule. And this is a constant called the Boltzmann constant. Boltzmann is a very important scientist person when it comes to molecular level analysis. And a lot of his ideas are actually used here. So, we have one part of it. We have the speed. What should we do next? Let's see what are the effects of collision, right? We have two types of collisions. Or how can we characterize collisions? We have a collision of molecule by one molecule. And then we have the collision of, we have one molecule colliding with a plate. That is actually very important for us because molecules colliding with a plate here is going to give us an idea of pressure in the macro scale. So pressure is essentially a bunch of molecules colliding with a flat plate, right? So we need to characterize this as well. The frequency of these collisions is characterized by 1/4 eta multiplied by the average speed. This eta here is the number density of molecules. Is there anyone in class who can tell me how we can find the number density of anything? How can we find density?
Number divided by the volume.
Number density, then density itself is mass divided by volume. When we say number density, is number divided by volume. Did you want to say the same thing?
I figured, does it have something to do with moles?
We are going to get there. But I mean, we don't really use moles in mechanical engineering at all. But yeah, number density eta is equals to number of molecules present in a system. Molecules present and volume of that system. If you multiply that by the average density and then divide it by 4, you are going to get the frequency of a flat plate bombardment. So this is the frequency of a flat plate bombardment. Frequency of a flat plate bombardment. But why is there a 1/4 there? Can anyone tell me? Think about it. If you multiply this number density by the speed, what would you get? Exactly, you will get the bombardment of all of the 4 plates, right? So you just have to, since this is a statistical analysis, we are just going to assume that the bombardment of all plates, all sides, are equal essentially and divided by 4 to give you the bombardment of one flat plate per unit area. Keep that, this is also per unit area. Okay. Again, the goal here, I'm just introducing these things to eventually connect the kinetic energy of the system, the internal energy of the system, to its temperature, right? So we are just introducing this. If you are not following, make sure to ask questions. Let's look at these two molecules here again. As I said, most of the time of these molecules is spent between one collision and another collision. So the distance between the two is important, which we call the mean free path. This is the distance, the average distance again, between two collisions. And mean free path, lambda, can be calculated as 1 divided by a square root of 2 eta sigma squared pi, right? Yeah. This sigma squared is the diameter of our molecule. The sigma itself is the diameter of molecule. So lambda is a function of your number density. Mean free path is a function of number density, your diameter, and also pi. These have extensive proofs, but we are not going to get into them because you need some statistical thermodynamics background to be able to do this. But let me, before moving on, let me see if anyone in class has any idea about the diameter of a molecule. How can we measure the diameter of a molecule? Does anyone know?
Well, we read I read somewhere earlier. So it was something to do with it was the distance between two molecules and then dividing that by two, something like that.
Yeah, so we essentially what we do, of course, the measurement devices, you're not going to use a ruler there. There are like measurement devices you need to use. And you have these are two molecules that are just beside each other. You can identify the center of each molecule, right? But you can't really identify the boundary. So you can't just measure from this to this and come up with a diameter. But you can find the distance between the two centers. That is going to give you the diameter of each molecule, because we are going to assume that molecules are circular and have the same size, right? Molecules of one specific material, like whatever the material is. So keep that in mind. When we have the mean free path, we can actually also find the time it takes to get from one molecule to another molecule. How can we find this? Let me see if there is anyone in class who can answer this question. We have the distance between the two collisions. How can we find the time it takes from one collision, one molecule to other molecule?
Find the average speed.
That's it, right? Pretty plain and simple. Lambda divided by the average speed. This is called the relaxation time. Relaxation. Is it relaxation time? And 1 over this tau is going to give us a representation and understanding of collision rate. Okay, so based on what we already have, let's see if we can come up with an idea or if we can quantify pressure on a large scale. And let's do it together. Pressure. We have the molecular level presentations. What do you think pressure is on a molecular level? I just said it, I guess, 10 minutes ago. What do you think pressure is?
The amount of collision with the flat plate.
The amount of collision with a flat plate. So essentially, the force that is caused by that collision, right, per unit area is the pressure, right? So how can we quantify it? How can we find this collision rate here? So the number of molecules present here is important, right? The number density is important. So we are going to have n. I assume their mass is going to be important as well, right? What else?
Speed, how fast they are moving.
It is very reasonable to assume that speed is also important. Number density is actually the variable we are interested in. So n divided by volume of the container. And this is divided by 3. There is a bonus point hidden here. If you can explain to me, why do we have this 1/3? First of all, let me ask you this. Mechanical engineers, we have all passed fluid mechanics. Some of us multiple fluid mechanics courses. Is pressure a scalar or a vector? Or is it a vector? Scalar. Do we all agree? So pressure, how do we define pressure in large scale? Force per divided by area, right? Force is a vector.
I would say pressure is a vector too.
Pressure is a vector.
Maybe I'm not sure.
So we have one scalar, one vector. Hands up for pressure is a vector. 1, 2. So those of you who say it is not a vector, you have to explain, you have to elaborate. Why is it not a vector?
Pressure at one point accessing in all directions.
So yeah, exactly. So pressure is always normal to your plate, right? Or due to whatever that plate is. And also, if you want to explain it mathematically, force is a vector, but also area is a vector. Area is not a scalar. So pressure is scalar. So essentially, if your plate is like this and you have your fluid here, pressure is going to be in this direction. But if your plate is like this and you have fluid here at the same location, pressure is going to be in this direction, right? So although we use vectors to present pressure, but it is not a vector quantity. It is a scalar quantity. Keep that in mind. Okay. So let's go back to this. Why do we have 1/3 here? And you have until the end of this lecture to just give me an answer. You can just put your hand up. Give me the answer for this. I'm not going to wait on it right now, but just keep in mind that this bonus point is here. Do we know how bonus points work? Did I explain this? Yes. You want?
Just because there's 3 dimensions.
3 dimensions. How can you relate this to?
Like it's 1/3 in the x direction, 1/3 in the y direction, and 1/3 in the z direction.
You are getting warmer. It's not quite correct, but yeah, you are getting warmer. It is related. You'll get the bonus point though. So Daniel got the bonus. See, a degree in chemistry helps with molecular representation, right? Yeah. Okay. So what happens here is that we have velocity in different directions, right? We have the component of velocity in x direction. We have the component of velocity in y direction. If we are dealing with Cartesian coordinate systems, of course. We have the component of velocity in the z direction, right? Because of our assumptions and because of the way we are looking at this, which is a statistical type of analysis, these are all equal to each other, and they are all equal to 1/3 of c. But it's not this simple, actually. The square of all of these velocities are equal to each other. So essentially, in any direction we are moving, your velocity should be 1/3 of your c, right? Your average total velocity of the whole system. And this is the reason we have here pressure. Let's say this is a flat plate. The velocity moving is in this direction is 1/3 of c squared. This is why we have 1. And you will see in a statistical analysis, you will see this 1/3 a lot. We are not going to go into a statistical thermodynamics in this class, but you will see this 1/3 a lot. And that's a very simple explanation of it. So don't hold me to it. Okay. I have one more question before moving on. Why do we have the square of velocities instead of the velocity itself? Why is this a square of velocity? Why don't we just simply say the velocities are the same in every direction?
You can have a negative.
You can have a negative. What is the problem with the negative velocity?
It's going different direction.
So velocity is a vector. Negative only means that it's a different direction, right?
Yeah.
So that doesn't really cause any problem here.
Because they're trying to understand the magnitude?
Yeah, it's because it's a vector. And wouldn't it just boil down to the Pythagorean theorem?
No.
No.
You're trying to assume that the collisions go in one direction.
No.
Does that have to do with the root mean squared?
Root mean square. Okay, you're getting warmer. I mean, not really, but it's just. Did you want to add something? No. Anyone else? So whenever you see this, when you're talking about averages in general, whenever you see this, and your type of analysis is a statistical analysis, think of a standard deviation. Right? How do we define a standard deviation? Does anyone remember? It's the square root of
The sum of the difference between the average and the value
squared, right, divided by n.
Or
Why do we have this square root here?
To keep it positive,
yeah.
Just to make sure, not to keep it positive, just to make, because if sum of x minus xi's
You don't want that to be zero.
is always 0. To make sure we have a non-zero standard deviation, which is true, which is a true form of a standard deviation. Standard deviation is not 0 in a data set, right? We have to take it to the square, right? We have to take it to the power 2. And the same idea applies here. Okay? Again, we are just trying to give you a very simplistic explanation of what is going on here. So, we understand the frequency, we understand pressure, we understand relaxation times, a mean free path, and also the velocity. Let's go to the energy. Kinetic energy, the average kinetic energy of the system is 1/2 mc squared. Something we knew. And just instead of v, we are going to have c squared, right? If we play with these two equations a little bit and write it and solve it for PV, pressure multiplied by volume, we're going to get pressure multiplied by volume is equals to 2/3 of number of molecules present multiplied by the average energy, average kinetic energy of the system. And since we are dealing with gases, we also have the ideal gas law, which is N multiplied by the universal gas constant multiplied by temperature, ideal gas law. So we have one temperature present here in the ideal gas law. What is the universal gas constant? Does anyone remember?
Like the number or
The number, yeah, the number.
8.314.
Exactly, 8.314. This is the universal gas constant. And what is the N here?
Number of moles.
Number of moles present in the system, exactly. And we have different types of ideal gas law, so you can actually have it as a function of density or number of moles or even your mass, different variations of ideal gas law. But this is what we are going to work with, right? And how is this related to the total number of molecules in the system?
Avogadro's number?
It is related to Avogadro's number. How is this related?
It's just
It is not equal to Avogadro's
capital
number.
N divided by lowercase n.
Capital. So
Right
we
there.
define the Avogadro's number as the number of all molecules divided by number of moles, right? Okay. And we know what the Avogadro's number is, right? What is it?
6.023
10 to the 23, right? 6.022 times to the 10 to the 3. So we have two relationships for PV, and we can set them equal to each other. And we can have a relationship between the average kinetic energy of a system and temperature. It's going to be 3 divided by 2 Boltzmann constant multiplied by temperature. And this Boltzmann constant is actually replacing the universal gas constant divided by Avogadro's number, which is 8.3143 divided by 10 to 23. And it is actually 1.38 10 to the negative 23. The unit is joules per Kelvin. So we achieved what we want to do, what we wanted to do. We related the kinetic energy of the system, the average kinetic energy of the system, to its temperature, the average kinetic energy of a molecule to its temperature. Okay? Any questions so far? This is the average kinetic energy of a molecule. Average kinetic energy of a molecule. Molecule. Okay? How can we relate this to internal energy? How can we relate this to internal energy?
Total energy minus kinetic energy is equal to internal energy.
You are talking about the macro scale thing. Total energy minus kinetic energy, right? Well, the energy here of each molecule is only kinetic energy. There is no other energy for a molecule, right?
Okay.
So how can we relate the average kinetic energy of one molecule to the internal energy of a bunch of molecules, which make the system? Yes. Multiply by the number of molecules. That's it. So internal energy of the system is N multiplied by the average kinetic energy, which is equals to 3/2 number of molecules, Boltzmann constant, multiplied by temperature. We can also, if we massage this a little bit, we can also find a specific heat at constant volume. From the kinetic energy, it's going to be 3/2 Boltzmann constant divided by M. Just have this as a side note. Okay, so we have the relationship between the internal energy and temperature of the system. So we understand, at this point, we understand that temperature is just another form, another representation for the amount of internal energy of a system. Okay? We can also relate the viscosity to the temperature. And the relationship is like this. 2 divided by pi to the power 3/2 multiplied by the square root of M, Boltzmann constant, temperature, divided by the diameter or the cross-section, cross-sectional length, squared. We also can have the same thing for conductivity in a system. Boltzmann constant cubed divided by M. And also diffusivity of a system. I just gave you the equations here because the proof of these equations is actually on you. And these are the only proofs that we have in this course. I mean, proof is a strong word. You just have to play with the equations to get the final equation. You don't have to start from a base thing. So viscosity, conductivity, and diffusivity.
saying like these are proofs we should bring to class, bonus points, or like something?
So one of them actually we are going to do right now
Okay.
as a quiz. So, and the other one is part of the homework. And third one we don't need to prove because we don't really do diffusivity in this course. Okay? So let's do it. If you recall from the first lecture, I told you that the attendance is checked by random quizzes. You don't really need to have a correct answer for a random quiz. You just have to show some effort. That's it. And we're going to have the first random quiz right now. So I want you to get to this, derive this equation for me, the viscosity equation. And we're essentially going to, what's that? I do have a pen. There you go. You can tear a paper out of your notebook. And if you don't have papers, there is some here. These aren't mine, but I guess no one's using them. So if you don't have paper, there's some here. And we're gonna work on this together, essentially, but we are gonna spend 10 minutes. Let's do 10 minutes on this. Okay. So we wanna prove the viscosity equation. Again, this is the kinetic theory of gases. So you have to go back to your knowledge of gases, right? How can we relate to the viscosity to force, let's say? How is viscosity related to force in fluid mechanics? Does anyone remember? Does anyone remember the Couette flow? You have a plate that is moving at U infinity and a stationary plate.
Is it like shear force times the du by dx?
Shear force,
So equals viscosity times du.
that's it, right? There's a shear stress here. This is how it is related to force, right? If you recall from the, do we know what Couette flow is? Yes or no? No, we have one no. No, that's all right. Just forget about it. So let's start. We want to start with the force balance. Just forget about the Couette flow. We'll try another approach. Let's say you have this coordinate system, x, y, and z, and you choose a small element in your gas, and your gas is moving, right? Because it's a fluid, we have layers moving on top of each other, right? This element, we have some force exerted on this element, some shear force exerted on any element of any part of this element, this a small element of gas. Does this make sense? So this is essentially a control volume. Are we following? Yes. Okay. Tau. Does anyone remember how to calculate shear stress in fluids? We have one no. No. It was related to viscosity and the gradient of velocity. Does this make sense? Okay. So this force this shear force is going to be tau multiplied by A, or mu viscosity du dy multiplied by the area, this area specifically. So delta x, delta z. I'm sorry. So the total amount of forces that are applied, we are only looking at this upper side of the contour volume. Total amount of forces applied to this is shear stress multiplied by the area, right? Viscosity, du dy, and there is no other forces. Is there? There we don't have gravitational force. We don't have the shear force is the only force present there. What can we say about this right-hand side? What is force equal to? Net force. Mass ma. Exactly. So mass times acceleration is equals to okay. Let's see if we can go any further from here on our own. Just keep in mind A is the derivative of velocity with respect to, in this case it is respect to y. This is derivative of just go back to your equation and see where m is, where you can find m. If you can see if you can change these equations to solve for m and replace m with anything. Because that's the clue. And keep in mind, this is a very hard problem. So if you can't solve it, don't be scared. That's why we are doing it in class together, right? If you go back to the main equation here, you can see that this is a function of your cross-section and temperature, right? This viscosity. So there should be somehow some sort of a representation of cross-section. And one other thing that you need to keep in mind here is that this m is not the mass of one molecule, it's the mass of the whole element. So mass of one molecule multiplied by the number of molecules, volume should be present there. Let me actually use large m to make sure everyone. Any ideas? No?
How can we find the relation of velocity while it's not a function of y?
You don't need to. They cancel out. So essentially, the only thing you really need to find is the mass of the molecules that is hitting the plate, right? From both. Keep in mind that these molecules are hitting that plate from both sides. But this is a fictionary. This is not a real plate. So we have some molecules coming into the element, some molecules going out of the element. So whatever mass you can find for it has to be multiplied by 2. Of course, mass of the molecule itself, each molecule is going to play a role here, right? Total mass of the molecules hitting the plate, mass of each molecule should play a role, right? Makes sense. What else plays a role here? Number of molecules that are hitting the plate at each time. What do we call this? Per unit time. Number of molecules hitting the plate at each time. Per unit time.
Relaxation.
No.
The frequency.
Frequency, exactly. Frequency. So mass of each molecule, frequency of the bombardment should play a role here. What else? Again, let me magnify this. I'm going to magnify it here. This plate, this is a boundary, this is a control volume. So molecules can come in and go out, right? Molecules are coming in and going out at a rate. And the distance, actually I should have told you this. The distance each molecule travels until it reaches another molecule is lambda. But the distance it travels until it reaches a plate, or a plane in general, is smaller than this, is 2/3 of lambda. So if you were to use that distance, make sure you are using the correct value, not the lambda, or the 2/3 of lambda. Which I think we are a little, I don't think anyone has arrived there yet. Okay, let's do this. Because we need to think about it a little more, about this problem a little more. This is what we are going to do. I'm going to gather your submissions essentially, because they are going to go towards your attendance grade, right? But work on this and try to solve this, right? Bring the solution to me, and you should be able to explain your solution. There are millions of solutions to this problem online, so you can just go and copy. But if you can't explain it to me, you won't get the bonus point. So make sure to submit whatever you have right now to get the attendance point. If you don't, then I won't give you the attendance point, man. Because I won't know if you were here or not. But take this home, try to solve this, bring on Tuesday, and if you can explain your solution, then you will get a bonus point. 2 bonuses we have had. One of them Daniel got, and the other one everyone can get. So it is not specific to the first guy. It is not a first come first serve thing. So anyone who submitted this, who submits this, will get the bonus point. Any questions? So let's talk about the project a little bit, and then you'll be free to go. The class will be dismissed. Is there anyone who doesn't have a group partner yet? So Mohammed, what was your name? Luke, yeah. Mohammed and Luke. You are the only ones who don't have a group partner. So, who else? You. You have 3 people in class. So, the 3 of you talk to each other. We have 18